Okay, so welcome to week 4 of these weekly discussion sessions on the course Foundations of Our Software. Now, before starting today's discussion, there's one small announcement that I would like to make. Next week, we will not have a session on Saturday. So, as a matter of fact, we will not have any discussion session next week. The Saturday discussion which is dated 27th August, will be postponed to Tuesday, 30th of August. So you will get an email from the NPTEL team also. The Google Meet link will stay the same. The timing will also stay the same, 5 p.m. to 6 p.m. But instead of Saturday, 27th August, we'll meet on Tuesday, 30th of August. Okay, so let's start discussing this week's lectures. I'll start sharing my screen. And please let me know if at any point the screen vanishes or if I am inaudible. So, as of right now, all of you can hear me and you can see the R Studio window on my screen.
Yes, sir.
Okay, thank you.
Yes, sir, we do.
Okay then. So, the starting point of this week's lecture is basically what was the ending point of last week's discussion, which was matrices. How do we define matrices in R? I mean, to start with, what exactly matrices are? How do we define them? Why do we need them? So, let's start by looking at how we define matrices in R. So, let's say if we want to define an object M, which is of the matrix variety, then we need to supply some arguments to this function. So first of all, we need to say how many rows do we want in the matrix. Then we want to specify the number of columns in the matrix. Let's make it 3. And then we want to specify what kind of data do we want to fill our matrix with. So important thing to note is that number of elements in the matrix is actually the product of the number of rows and the number of columns. So we have 2 rows and 3 columns. So we'll have 6 elements. So a good starting point is, let's populate these 6 elements with the numbers from 1 to 6. So you see that an object is created here in the global environment. And now if you write M, you can automatically see this structure. So there are a few things that we need to note from what is displayed on our screens. First of all, what is the manner in which the data is being filled? So we just said that fill in the data, which is the numbers from 1 to 6 inside of a 2 cross 3 matrix. So again, this is the language that you need to be familiar with. When we talk about matrices, we usually talk about N cross M or P cross Q or A cross B. I mean, you can use whatever variable you want to use, but there's something multiplied by something. That is the way we talk about matrices. So the first thing is the number of rows, the second thing is the number of columns. So here we have 2 rows and 3 columns. So whenever we are talking about this matrix, we can refer to it as a 2 cross 3 matrix. And that basically means that we have 2 rows and 3 columns. We will not change convention. We will not refer to this matrix as a 3 cross 2, because that would have meant that the number of rows is 3, number of columns is 2. So we want to be uniform in our discussion. So whenever we refer to an N cross M matrix, what means is the number of rows is N and the number of columns is M. So in this case, number of rows is 2, number of columns is 3. So, like I said, we want to populate this 2 cross 3 matrix by these 6 numbers from 1, 2, 3, 4, 5, 6. Now notice, by default, the way R is populating this matrix is column wise. So it tries to fill the first column first. So there is 1, 2, then it goes to the second column, 3, 4, and then to the last column, 5, 6. Now what happens if, let's say if we create a second matrix and we call it, let's say we call it M2. And instead of the number of entries, if the number of entries is less than the maximum number of elements that the matrix can hold. So if I make the data from 1 to 5, what happens then? So you see, R throws a warning. It shows that this is not a multiple or submultiple of the number of rows. So, and what it does, so if we write out M2, you see, it fills in up to 5. So 1, 2, 3, 4, 5. That works. And since it has run out of data, it starts at the beginning again. So it goes back to 1. So again, if this was just 1 to 4, let's say, it will again show the warning. And again, it will fill up to 4, 1, 2, 3, 4, and then repeat from the beginning, 1, 2. Now, usually it's not a good idea to, give incomplete data to the matrix and then expect R to do the right thing, because what is the appropriate action in your mind may not be the appropriate action in R's mind. So it's very important to be clear at every step. So while defining a matrix, we should try to be as clear as possible. So what happens if we do an overflow? So let's say we say 1 to 7. So now it says that, okay, again, the length is not a multiple or submultiple. But if we access M2, we see that it has filled in what it could fill in. So we had space for 6 elements, so it has filled in up to 6, and the last one it has discarded. But again, this is, whenever you get a warning, it means what you are doing is risky. So try not to enter data in a manner which leads to warnings. So we want to stay away from warnings. So a rule of thumb while defining matrices is that the number of elements equals the number of rows multiplied by the number of columns. So the data that we are supplying should contain, the correct number of entries. Now, another thing that you can notice from the way these matrices are displayed is that whenever there is a column, it is writing comma 1, comma 2, comma 3. And whenever there is a row, it's writing 1, comma 2, comma, and so on. So what should be clear from this is, if you remember last time what we had discussed is how to access specific elements, right? So if you write M2 1, comma 2, then that gives 3. How do we read this? So M2 1, comma 2 means that look at the first row. Within the first row, look at the second column. And what is the element sitting there? So this is 1, this is comma 2, which is 3. And that is what it is returning. But instead of 1, comma 2, if I just put 1, comma nothing, it will basically return the entire row. So that's what this 1, comma 2, comma means, that if you give this information, this is tagging your row basically. So this is the first row, second row. So if you just want to access the entire row, you put the row number, comma, and then nothing next to the comma. Similarly, if you want to access, let's say, the second column, now this will give you the elements of the second column. But again, one thing we should be careful about, the way the output is being printed here, when we are calling for the specific row or if we are calling for a specific column, it is still printing horizontally. So if you just write 3 and 4 here, it's hard to know whether that belong to a row or column, because in the matrix the columns are written vertically, the rows are written horizontally, but when you call for the specific elements, they're all written horizontally. So again, it should be clear what we are asking from R and exactly what R is giving us. Now there is one next step from this. So we saw how to access an element, a single element. We saw how to access an entire row, and we also saw how to access an entire column. But as we can see, this 2 cross 3 matrix does not only contain individual elements, it has subparts which themselves can be thought of as matrices. So we'll call these subparts as submatrices. So from M2, let's say we want to from M2, let's say what we want is, we want the first, starting from the first up to the second row, and also starting from the first up to the second column. So what this returns is a 2 cross 2 sub-matrix of the full matrix. So in some languages or in some communities, this is also known as slicing the matrix. You are mentioning a slice that you want to be returned, just like cutting a cake. Now, when you do the slicing, let's say in the column way, okay, let's work with a larger matrix so that the slices can also show some varied feature. So let's say we are working with 4 rows and 4 columns, and we fill in the data from 1 to 16. So now we can take different slices out of this. So from M3, one thing we can do is, okay, we want the, starting from the first column, we want up to the third column. So 1, 2, 3. But as far as the, row. So starting from the first row, we want up to the third row. And as far as the columns are concerned, let's say we start from the second column and go up to the fourth column. So if we do that, now here then this naming of rows and columns will not match what was there previously, because this is for the fresh matrix. This does not reflect what is coming from the older matrix, but what reflects the signature of the older matrix is the entries. So what did we ask for? We asked for the first row up to the third row. So first, second, third rows. And then second row up to the second column up to the fourth column. So we are rejecting the first column and we are rejecting the fourth row. And what that leaves us with is exactly this 3 cross 3 block. So you have 5, 6, 7, 9, 10, 11, 13, 14, 15. Okay, so when you do this range-based calling, this will give you continuous rows and continuous columns. So the second, third, fourth column, first, second, third row. But you can again call for them as collections. So let's say I want the first and fourth row, and I want the second and third column. What do I get? So again, pay attention to this. So first row, the second and third column. So 5 and 9 are there. Then the fourth row and second and third column. So 8 and 12 are also here. So these are some of the ways in which you can manipulate the rows and columns or the entire matrix. Now, again, keep one thing in mind. While doing these operations, we have not stored these new matrices in any variables. So M, M2, M3 are still the same as we had defined them. So while doing this slicing, the original matrix does not go away unless you overwrite it. So unless you do something like take this slice and store this inside M3 itself. So now M3 has changed. Now the original M3 is gone. If you don't want the original M3 to go away, you store this slice in a new variable. Now, one thing I mentioned last time, why do we need matrices? Why do we work with matrices? And one of the reasons is that we can see a very clear tabular structure here. So this is very good for storing data. So, simplest example could be entering marks obtained by some students. But if the matrix is written like this, 1, 2, 3, 4, 1, 2, 3, 4, how would I know what is marks and what is student name or something like that? So what we can do is rename the rows. So okay, let's come back to the matrix M, and there is a function called row names, or M, which allows us to give specific names to these rows. So for simplicity, let's keep them R1, R2. Now what happens because of this? If you call M once again, You see, instead of this 1 comma 2 comma, this is R1 R2 now. Similarly, you can add column names. So we just put COL names. There are 3 columns, so we'll give 3 names. Now if we call M, so this is both row names and column names. So now this way you can organize your data, I mean to reflect exactly what you want to reflect from this. Now one more thing related to this, as we have seen, automatically R fills in the data column wise. But what if I want to change that? So let's say, going back to the definition for M, if we wanted these numbers to be filled in row wise, what we would do is we'll just set this by row equals true. So now if I look at M, is 1, 2, 3, 4, 5, 6. Now remember, this C1, C2, C3, R1, R2 are gone because we redefined M. So whenever you redefine the variable, it is defined from scratch. So okay, so when we are discussing matrices, we need to discuss concepts that are related to matrices. One of those concepts is that of a diagonal matrix. So what do we mean by a diagonal matrix and how do we create it? So let's say we look at a matrix with equal numbers of rows and columns. Let me call it M4. We put 3 rows, 3 columns and populate it with numbers from 1 to 9. So this is M4. Now what we want, so you see, there are this part of the matrix, the 1 comma 1, the 2 comma 2, the 3 comma 3. Basically the entries which have the same row number and column number, these form what is known as the diagonal of the matrix. One way to create a diagonal matrix is by explicitly giving entries like this. So let's say I'm giving a collection. I know that this will be filled row wise because I've set by row equals to true. So I know 1 comma 1 will be filled first, then 1 comma 2, then 1 comma 3, then we'll go to 2 comma 1, then 2 comma 2, then 2 comma 3 and so on. So accordingly, let's say the first element is 2, the second one is 0, the third one is 0, then another 0, then 3, then 0, then 2 more zeros, and lastly we have something called 9. Now if you put M4, you see, only the diagonal entries are non-zero. Everything else is 0. So a matrix of this type is known as a diagonal matrix. But we don't want to go through this again and again. I mean, we don't want to count how many zeros will be there and then accordingly put zeros in our data entry. So there is a simpler way of doing this, and that's especially useful if, you know, we are building larger matrices. So say if the diagonal contains the same element again and again, so then a good way to populate this, let's say we want to populate the entire diagonal with just ones, and we get n row equals 3, n col equals 3, then you get a diagonal matrix like this. So let's see, this is something I have not checked, I'm only checking right now. Can we give it a collection? Will this work? Yeah, so this also works. So if you have a very large matrix which only contains diagonal elements, you don't need to fill in all the zeros by calculating at what position there should be a 0, at what position your diagonal entry will go. You can just give the collection of the diagonal entries and use this diag command instead of the matrix command, and you'll get a diagonal matrix. So what else can be done with matrices, or what other commands are relevant as far as matrices are concerned? So that can be seen from the definition itself. So okay, here both number of rows and columns is 3 and 3, but what if I want to exchange that? What if I want to, convert this 2 cross 3 matrix into a 3 cross 2 matrix? Or staying within this 3 cross 3 matrix, what if I want to exchange the row and columns? So that operation is known as taking the transpose of your matrix, and the simple command for transpose, which is just T. Now I want someone to answer this. What happens if I take the transpose of a diagonal matrix? What will I get?
The same matrix.
The same matrix, because at these opposite positions, so by opposite positions I mean 1 comma 2 is the opposite of 2 comma 1, 1 comma 3 is the opposite of 3 comma 1, 2 comma 3, 3 comma 2. So you get the idea. So in the diagonal matrix, in the opposite positions we have the same number, which is 0. So if you do the transpose, it will return the same thing, because as far as the diagonal entry is concerned, it will stay intact. 1 comma 1 is still 1 comma 1, 2 comma 2 is still 2 comma 2. But now let's do this operation on M4. Okay, so M4 was also diagonal. Okay, I rewritten this. So let me redefine M4 from here. Okay, so this is M4, and this is the transpose of M4. So if you look carefully and compare, you can see the diagonal entries stay the same. So 1, 5, 9, still 1, 5, 9, but 2 and 4 have exchanged their positions. 3 and 7 have exchanged. 6 and 8 have exchanged. Now if you do the same thing to, so this was a square matrix. By square matrix I mean the number of rows and number of columns is the same. It looks like a square matrix, so we call it a square matrix. Now if you do it to a rectangular matrix, where the number of rows and number of columns is not the same, you basically exchange the number of rows and number of columns. So what was previously a column, so this one, a row, this 1, 4 was a row. Sorry, I'm going in the opposite order. So this was M, 1, 4 was a column. Now 1, 4 becomes a row after the transpose. 1, 2, 3 was a row. 1, 2, 3 now becomes a column. So this is a row column exchange. But what also changes for rectangular matrices is the way we'll talk about it. So this M was a 2 cross 3 matrix. Transpose of M is a 3 cross 2 matrix. So that difference must be understood. Now there are additional operations additional functions provided by R that can make our life easier in some cases. So let's say we want to know what is the sum of each of the rows of a given matrix, or each of the columns of a given matrix. So there is a command called row sums. So if we evaluate this on M, we have 2 rows, that's why it's giving us 2 answers, each corresponding to each of the rows. So first row, it is 1 plus 2 plus 3, that is 6. The second row, it's 4 plus 5 plus 6, which is 15. We can do the same thing for columns also. So again, we have 3 columns, that's why we are getting 3 answers. So 1 plus 4 is 5, 2 plus 5 is 7, 3 plus 6 is 9. The next thing, similarly, what we can do is we can calculate the means of each of the rows. So 1 plus 2 plus 3 is 6. We have 3 entries. So 6 divided by 3 is 2. Similarly, here we had 15 and 3 entries. So 15 divided by 3, we have 5. And again, the same for columns. So now 1 plus 4, 5, 2 entries, so 5 divided by 2, 2.5. Again 7 divided by 2, 3.5, 9 divided by 2, 4.5. There are many more such easy to use functions available inside R, which make it easier for us to do some mathematics with matrices. Now we'll basically now move on to, after studying the features of a matrix, we'll move on to doing some arithmetic operations on it. So previously also, while introducing R, the first thing we had looked at was scalar operations. Then we introduced something called vector, and we had looked at vector scalar operations before going to vector operations. So as far as matrices are concerned, we'll first look at a matrix and a scalar operations. So let me clear the screen, and let's say we stick with this matrix M, and we define a constant number, let's say 5. Now we want to see what happens if we try to do some operations between M and A. So I hope you guys remember what was happening when we were doing scalar operations with vectors involved, or vector plus scalar, or vector multiplied by a scalar. So can anyone mention what was happening in those cases?
Multiplied by all the entries of that vector.
Right, so it was an element wise operation. So we had, the scalar was basically a special case of the vector. You had only one entry. So it will, if you do the addition, it will get added to each of the elements. If you do multiplication, it will get multiplied to each of the elements. Similarly, if you do M plus A, you see what happens is this 5 is getting added to each of the elements. So 1 plus 5, 2 plus 5, 3 plus 5, 4 plus 5, 5 plus 5, 6 plus 5. So same thing happens if you do a subtraction. It will be an element wise subtraction. If you do a multiplication, it will again be an element wise multiplication. Division will work in the same way. What about these some special operations that we had looked at? What if we try to take a power? Again, this is doing an element wise operation. So 1 to the power 5 is still 1. 2 to the power 5 is 32. 3 to the power 5 is 243. And same way for 4, 5 and 6. That you can check by explicitly doing the multiplication. Similarly, you can do the modulo operation. So if you remember, the modulo operation basically gives the remainder if a given number is divided by the other number. So 6 is 5 times 1 plus 1. 7 is again 5 times 1 plus 2. And similarly, 10 is 5 times 2 plus 0. So these are the remainders you will get if you divide each of the entries in M by 5. Okay. So let's see if you can do some other operations that we were doing. So can we check if the matrix is made up of integers? So it is. The reason being, we had defined this matrix using this range notation, and this range notation automatically fills in with integers. So let's move on to matrix operations. So we have M, we have M2. Now remember, the difference between M and M2 was one of them was filled row wise, the other was filled column wise. So what happens if we try to add M and M2? You see, again we'll get an element wise addition. So 1 gets added to 1, 2 gets added to 3, 3 gets added to 5, 4 gets added to 2, 5 gets added to 4, and 6 gets added to 6. So again, if we do a subtraction, So because 1 and 1 the same, so 0, 6 and 6 the same, so 0, and other places the subtraction takes place in the usual manner. And again, if we do this m times m2, once again what is happening is an element wise multiplication. So this 1 times 1 is 1, 2 times 4 is 8, 5 times 4 is 20, 2 times 3 is 6, 3 times 5 is 15, and 6 times 6 is 36. What happens, let's say if m2 is not of the same size as m. So we have seen these issues before, that what happens if we try to populate the matrix with less number of elements. What happens if we try to do operations on vectors where one of the vectors, the size of one of the vectors is a multiple of the size of the other vector. What happens if that's not the case? So let's define a new matrix, let's say, or we don't need to define a new matrix. We have M3, which is a 2 cross 2 matrix, and M. Let me clean the screen again. M and M3. So N and M3 do not have the same size. So if we try to add them, see, this time R will not make an adjustment. It will not add the corresponding elements and start at the beginning. It will just throw an error. So for these arithmetic operations, the shapes of the two matrices must be same for these matrix operations. Similarly, if we try to multiply them, we'll say these are non-conformable arrays. Okay. Now the next topic is a bit involved, and I want you to pay very close attention, because this concerns matrix multiplication. So what we have seen while doing m times m2, it's not a matrix multiplication. We are just taking two matrices and multiplying their corresponding elements. But matrix multiplication is something more complicated, and it's not possible to do matrix multiplication with any two matrices. So we can start with a simple example. So for simplicity, let me write this on the script. So I will not do an R operation here. I'll just try to explain what matrix multiplication is before we write some commands. So let's say we have one matrix which is 1, 2, 3, 4. For simplicity, we are only looking at a 2 cross 2 matrix. So let me write this on the side. So this is a 2 cross 2 matrix. Now, before going into multiplying a matrix with a matrix, a simpler case is multiplying a matrix with a vector. But again, there is a question: what kind of matrices can be multiplied with what other kind of matrices? Or what kind of matrices can be multiplied with what kind of vectors? So let's say this is a 2 cross 1 vector. And this is a 1 cross 2 vector. Now I'll make a statement, and I want you to think carefully about this. I'll explain why that statement is true. So okay, let's name these variables. Let's call this A, or okay, let's call this M1, meaning matrix 1. Let's call this guy V1, vector 1, and let's call this V2, vector 2. So the statement I want to make is this: this M1 times V1 is allowed, but M1 times V2 is not allowed. But I'm not done. V1 times M1 is also not allowed. But V2 times M1 is allowed. Now, why that is? So that is based again on the number of what actually happens in matrix multiplication and how the number of rows and number of columns play a role in that. So first, let me mention how the number of rows and columns play a role in that. So let's say if you have a n cross M matrix and you're trying to multiply it with a P cross Q matrix, where N, M, P, Q are all non-zero numbers. They could be 1, they could be 2, they could be anything greater than that, but none of them are 0, and of course they can't be negative. So if we try to do this multiplication, this is only permitted when we are looking at matrices, only permitted if M equals P. And the answer is N cross Q matrix. Now again, why that is so? Why do we need M and P to be equal? So what happens in matrix multiplication is that an intermediate step is element by element multiplication followed by an addition. That element by element multiplication will only take place if the number of elements is the same in the column that we are so let's say let me try to explain this with examples and why M1 times V1 is allowed but M1 times V2 is not allowed. So looking at just these N cross M values, it is easy to see. So if we look at M1 times V1, we have 2 times 2 again times 2 times 1. So this and this are same, so multiplication is allowed. But M1 times V2 is a 2 cross 2 matrix multiplied by a 1 cross 2 matrix. So 2 and 1 are not the same. So that's why it is not allowed. But if we do the opposite, V1 times M1, it becomes 2 cross 1 times 2 cross 2. Again 1 and 2, not the same. But V2 cross M1, so V2 times M1 is 1 cross 2 times 2 cross 2. So 2 and 2 are again the same. So that multiplication is allowed. But what exactly is happening during the multiplication? So let's just focus on M1 and V1 for the time being. What happens is, you look at the first matrix, start at its first row. At the same time, you look at the first column of the second matrix. And then you do an element wise multiplication and add. So what you should do is this 1 times 1 plus 2 times 2. What we are doing in matrix multiplication is building a new matrix using 2 other matrices. So we'll stay with the first row of the first matrix and we'll see, are there any more columns in the second matrix? So we see that this matrix had only 1 column. So there is nothing more to add. So we'll go to the second row. And again, we'll start from the beginning for the second matrix. So first row. So this is a 3 cross 1 or 3 times 1 plus 4 times 2. Now we have exhausted both the matrices. We had only 2 rows, we covered both the rows here. We had only 1 column, we have covered that column here. Now what does this become? 1 cross 1, 1 times 1 is 1 plus 4. 3 times 1 is 3 plus 6. Basically what we get is 5 and 9. And what we have obtained as a result of multiplying a 2 cross 2 matrix with a 2 cross 1 matrix, what we should have got is this times this. And that is exactly what we have got. A 2 cross 1 matrix. A matrix with 2 rows and just 1 column. This is what matrix multiplication is. Now, let's say to make it slightly more complicated, let's put 3 and 4 again here. So this is the same matrix. So we are doing M1 times M1. How this operation will change? So again, start with the first row of this matrix and first column of this matrix. We do an element wise multiplication and we add. So that gives us the 1 1 element of my new matrix. Now I'm staying with the first row, but I'm looking at the second column. This should give me the 1 2 element of this matrix. So this is 1 times 3 plus 2 times 4. Now I've exhausted the columns. So I'll go back to the first column here, but here I'll go to the second row. 3, 4 and 1, 2. So we do the multiplication for 3, 4 and 1, 2 and we add. Then staying with the second row, we move on to the second column of the second matrix. So this becomes 3 times 3 plus 4 times 4. So we add 1 plus 4 for this. We get 3 plus 8 from this. We add 3 plus 6 from this. We get 9 plus 16 from this. So this is 11. This is 25. And what we have is a 2 cross 2 matrix. So this is essentially what matrix multiplication means. Now, of course, this was a very simple example. We had just 4 elements in both of the matrices. So we could do this in a small amount of time. But let's say if you have a very large matrix, or you don't have to go very large. Even if you have a 4 cross 4 matrix, this process doing by hand takes time. So what we want to do is we want to let R do this problem for us.
Sir, so please can you just repeat the multiplication between the row and the column again?
Yeah. So first thing we need to identify is what is being multiplied with what. Okay, so here we are multiplying M1 with M1. So M1 is one matrix, M1 is the other matrix. So the matrix on the left, okay, one good way to write this is, so let's say, write it like this. So this is the multiplication that we want to do. This 2 cross 2 matrix 1, 2, 3, 4. 2 cross 2 matrix 1, 2, 3, 4. Am I still visible? I think my Wi-Fi is getting disconnected. Hello?
Yes, sir. Your screen is visible.
No, sir. It's very loud.
Oh, is it back now? I mean, my screen.
Yes, sir. Please share your screen, sir.
Okay, our studio is visible,
Yes.
right?
Yes, sir.
Okay. So focus on this. This is matrix 1, this is matrix 2. This is the first row of matrix 1. This is the second row of matrix 1. This 1, 3 represents the first column of matrix 2. This 2, 4 represents the second column of matrix 2. So this is what we are concerned with. We are concerned with the rows of the first matrix and the columns of the second matrix, not the other way around. So what matrix multiplication does is we pick this row. So again, we are trying to populate a new matrix which has the shape of 2 cross 2. Why is that? Because we are multiplying a 2 cross 2 matrix with a 2 cross 2 matrix. So n times m is being multiplied by p times q. So if m and p are equal, we forget about them and we want to populate a n cross q matrix. So in this case, n, m, p, q, everything is 2. So the result of multiplication of a 2 cross 2 matrix with a 2 cross 2 matrix is another 2 cross 2 matrix. Now, okay, I'll spend a little more time on this. So maybe we can dedicate today's discussion primarily on this matrix multiplication. Okay. So now that we have identified what are the rows of this first matrix and what are the columns of this second matrix, we'll do our operation. So in the new matrix, the 1, 1 element will be the element wise product of this row and this column, and we add that element wise product. So 1, 2, 1, 3. 1 times 1 plus 2 times 3. 2 times 3 actually. Okay.
Yeah, this is where I got confused, sir.
Yeah.
The
So
point with those and-
the source of the mistake was that earlier this vector was 1, 2. So that's what I stayed here. But okay, let's ignore this one. Okay, that was my mistake. I interchanged 2 and 3. That should not have happened. Yeah, so sticking with 1, 2 and 1, 3. So we multiply 1 and 1, we multiply 2 and 3 and we add. Now we stay with row 1, but as far as the matrix 2 is concerned, we go to the second column. So 1 times 2 and 2 times 4. Now again, so we have exhausted the first row and we have looked at both the columns of the second matrix. So we move on to the second row. So 3, 4 and 1, 3. So 3 times 1 and 4 times 3. And similarly 3, 4 and 2, 4. So 3 times 2 and 4 times 4. So I'll make the corrections as I move along. So this becomes 1 plus 6. This becomes 2 plus 8. 3 plus 12 and 6 plus 16.
So the screen has disappeared, sir.
No, sorry, it's okay.
So is it back for everyone?
Yes, sir. Yes, sir.
But the R Studio is not yet shared. Yeah, now it's back.
Okay. So 5, 10, 15 and 22. And we got our 2 cross 2 matrix. Now, a good exercise at this stage is you can just try and see what is permitted and what is not permitted. So, if instead of being a 2 cross 2 matrix, this was, let's say, a 3 cross 2 matrix. So let's put a 5 here and a 6 here. So let's forget about what's written below this line. Now you can see this is a 3 cross 2 matrix, right? Let me call this M2. Now if I try to do an operation on this, five and 6. Now there is a problem with this. It's very clear to see why there is a problem. So we are trying to multiply a 3 cross 2 object with another 3 cross 2 object. These two are not the same. So multiplication will not succeed because let's look at this explicitly. Let's look at the first row of the first matrix and the first column of the first matrix. You can do 1 times 1, 2 times 3, but what about this 5? This is extra. Same problem arises. Say if we fill these in differently, if we have a 2 cross 3 matrix. So again, look at the first row here, and the first column here. So you can do 1 times 1, 2 times 3, but again 5 remains. So this 2 times 3 times 2 times 3 is also not permitted because this 3 and 2 are not equal. But what is permitted? So you can multiply this 2 cross 3 matrix with a 3 cross 2 matrix. The reason behind this is that again, this number and this number are same. And this multiplication should ultimately give you a 2 cross 2 matrix. So now as you can see, this is the first row, it has 3 elements. It's the first column, it has 3 elements. You can multiply corresponding elements and then add. That will give you the 1 1 element of the resulting matrix. First row, second column, that will give you the 1 2 element. Second row, first column, 2 1 element. Second row, second column, 2 2 element. So what you get is a 4 element 2 cross 2 matrix by doing a multiplication of a 2 cross 3 and a 3 cross 2 matrix. So I hope I have explained which matrix multiplications are permitted and what exactly is meant by a matrix multiplication.
Yes, sir. Thank you. Thank you.
Okay, so let's see how R simplifies our task. So how is this done in R? So okay, what are the matrices that we had? We had M and we had M2. So I had mentioned that if we just do M asterisk M2, it will do an element wise multiplication. But if we try to do, if we want to do a matrix multiplication, we'll use a symbol, this asterisk sandwiched between two percentages. Now, before I execute this command, what do you expect? Will this work or not? Think carefully and then answer. Look at the shapes of the two matrices and then decide, can we do this multiplication? Anybody?
And the matrix operation is not possible because the first matrix has 2 rows and 3 columns, that is 2 by 3 order, and the second one is 2 cross 3 matrix. So the order in between does not match.
Right. So we need the number of columns of the first one to be same as the number of rows of the second one. And this gives an error as expected. But let's see if we have M3, which is a 2 cross 2 matrix. And now we try to do M3 times M. Will this work? Again, you have to apply the same line of reasoning.
No,
No,
No?
no, sir.
it will not. No, because again you get two by 3 and 2 by 2.
No. Look at the order in which I am multiplying.
M3.
I'm writing M3 first.
Okay. Yes, yes.
Yes, sir. Yes.
Right. So 2 cross 2 times 2 cross 3. So this will work. And this basically gives you an answer like this. So after doing the element wise multiplication, adding, and then it has prepared the matrix. Now, if I do M times M3, of course that will fail. Because that is 2 cross 3 times 2 cross 2. That will not work. Now, one more thing that will work is this. So, okay, let me write. So you see M4? And if I do M times M4, this works. Why? Because M is 2 cross 3, M4 is 3 cross 3. The result is also 2 cross 3. But M4 cross M shows an error. 3 cross 3, 2 cross 3 will not work. Now, again, let's say if we want to do a square the whole matrix, we cannot do that for M because M is not what is known as a square matrix. So a square matrix has the equal number of rows and columns. So if you multiply it with itself, it works fine. But you can't do that with M. Let's look at M4. M4 this will work. But what will work for M is that, remember, we also have the transpose of the matrix. And what the transpose does is that it flips the number of rows and the number of columns. So, and let's bring back our notebook. So, if a matrix has the order P cross Q, and I'm saying that the transpose basically interchanges the rows and columns, what will be the order for the transpose? Again, any one of you can answer this.
Q by P.
Q cross P. So now, looking at these two, do you think multiplication is possible?
Yes.
Yes.
Yes. So, if we do M, sorry, T acting on M, then this works because M is 2 cross 3, transpose of M is 3 cross 2, so 3 and 3 are the same, and we get a 2 cross 2 matrix. Now, if we do it in the opposite order, so we put the transpose first and then the matrix, multiplication is still allowed, but the answer is different. Why? Because the transpose was 3 cross 2, the matrix was 2 cross 3, the result is 3 cross 3. So this is again something we have to remember. So normally, if we do an operation on two elements or two objects, and if we do the same operation with the object's position interchanged, then if the result is the same, we say that the operation is commutative. So matrix multiplication in general is not commutative. So if you multiply two matrices in one order, even if they are square matrices, so it's not necessary that A times B and B times A will always be the same. They are same in only very some special cases. Now, this multiplication of a matrix with its transpose, this can also be simplified in R with a built-in command called the cross product. If you just write cross prod of M, it basically gives you this operation. So M transpose times M, that is what is referred to as the cross product. But this is simple, I mean, because you can specify if you want it, what order do you want. So you can do this explicitly, you don't have to use cross product. Okay, there is a question in the chat, and this is something that was mentioned in class also about the R bind and C bind commands. So let's see what R bind and C bind are. So again, this is M, this is M2. Now sometimes, sorry,
Hello, can you hear me, sir?
yeah.
Yeah. So actually, there is a command like R bind, concatenation,
Yeah,
R
yeah.
bind, C bind.
Yeah.
So I have one doubt. So there was I understood that R bind, what is R bind and C bind, but I have tried to do that assignment 4, but there is a question number 15. But I think whatever the problem it is given there, I think the order or something is maybe there is some typo or something like that. So there is no option, none of these above or something like that, or whatever I'm doing, there is error coming.
Okay,
Yeah, I
so
do that.
yeah, please go ahead.
So I too got the error answer for that question.
Okay, you have also received error. So what is the deadline for the submission of the assignment?
I think 24th, I think.
Okay, so I am allowed to discuss the assignments only after the submission date is passed. So I cannot discuss the fresh assignment solutions now. But in the next session, I can
Solution,
discuss that.
I think there is something, or maybe some typos, maybe. So
Okay.
that question is not we cannot solve, I think so.
Okay, so one thing you can do is mention this in the forum. So when you had joined the
Okay.
course, you must have received an email about a Google group, and so that email must have come at the very beginning after you had enrolled in this course. So on that forum you can mention, and maybe the instructor or one of the instructor's TAs, they can help with that.
So there is something, ask a question like in the lecture video.
Yeah.
So when the video was uploaded, there is option ask a question. So can we write in?
Yeah, you can write it down.
Okay. There also we can write.
Yeah. But remind me in the next discussion session, I'll discuss the assignments.
Sir, we can submit our assignments at any time or in a limited period, sir. Mentioned
There is a
by you.
deadline. So for every assignment, there is a deadline that is mentioned
Okay,
at the
okay,
very
okay,
top
okay.
on the right hand corner.
Okay, sir. Okay, sir. Thank you, sir.
Okay, so Yeah. So for some reason, if you want to, let's say there is one table where you have stored the marks of students in some three subjects. There is another table where you have stored marks in some three other subjects. Let's say these were prepared by different teachers. But while preparing the final grade sheet or the report card, you want to show the marks of all the subjects. So in that case, you want to concatenate the results. That is one example. The other example is in one table you have the marks of 5 students, the same three subjects but the marks of 5 students. In another table you have marks of 5 more students. So again, these lists were prepared by different people, but you want to have a unified list storing all these marks. So that is another scenario where you want to concatenate. But the manner in which we are concatenating the matrices is different. So in one cases, you want to attach the columns. So you don't want to increase the number of rows, you just want to add more columns to it. In the other cases, you want to add more rows, that's keeping the same number of columns. So that's where R bind and C bind comes into the picture. So if I do R bind on M and M2, you get a row wise concatenation. So the entries of M will be on top. So these first 2 rows are actually the rows of M.
So excuse me, sir.
Yeah.
So that means in the row bind, we're getting more rows because
More
we are
rows,
binding
yes.
the rows. So row wise it will be more.
Yes, yes.
And in the column bind, so we'll get more columns.
Yeah, exactly.
Right, but there should be something like that row and columns dimension or order there should be something like that, on which way I can add or I can row bind, I can do row bind or column bind, no, sir. So I think in question number 15 there is something, so it cannot error is coming actually.
So you're saying that that has to do with the size of the matrix? So probably.
Size of the matrix, yes.
Right. Yeah, that could happen. So because let's say if we want to do row bind on M and M3, the M3 was a 2x2 matrix. Okay, so no, row bind will be a problem here. Yeah, row bind is a problem here. That could happen. I mean, if there is a mismatch in
Yes,
size.
this kind of thing is there. Yes.
But
So
also
thank you.
make sure if there are brackets involved or if multiple matrices are being attached through row bind or C bind. Sometimes it may happen that okay, initially the two matrices could not be concatenated row wise or column wise, but if there is a multiple operation, so we do a C bind on 2 matrices and then we can attach that with the rows of some other matrix. So I'm not sure because I've not seen that assignment problem. But yeah, if you continue to face error, then please ask a question in the forum.
Okay, sir. Thank you.
Okay. Now there is another important concept that we must discuss when we are discussing about matrices. Let's say, now we saw what kind of matrices can be multiplied with what other kind of matrices. And we have seen that the easiest case is that of square matrices, because if the number of rows and columns is same, we can always multiply square matrices of the same variety. We can multiply any 3x3 matrix with any other 3x3 matrix. Same thing for any n cross n matrix. We can do the multiplication. So sometimes you come across the concept of identity. So let me explain this concept of an inverse based on some known examples. So if we are only looking at whole numbers, let's say, so 0, 1, 2, 3, or let's say we are looking at integers. So we also have -1, -2, -3 and so on. So we say that that we can add any two integers, and as far as integers are concerned, we will say that there exists an inverse with respect to addition of integers, or addition of integers is invertible. What does that mean? is that, first of all, there is an additive identity. What the additive identity does is that if you add that with any number, no matter how you add it, you get the same number. So the additive identity is 0. So if you add 0 with any number or any number with 0, you get the same number. Then the additive inverse is, so for a given number, so let's say we are talking about 2, then the additive inverse of 2 is that number which when added with 2 gives us 0. So that number for 2 is minus 2. So 0, as far as integers are concerned, 0 is my identity, additive identity, and the negative of any number is its additive inverse. So if we were talking about minus 2, then the inverse would have been 2. But if we were talking about 0, the inverse is 0 itself. So let's go a step higher, and we are talking about, let's say, rational numbers or real numbers. Then we can also talk about multiplication, and the multiplicative identity is 1. So if you do 3 times 1 or you do 1 times 3, you get 3. This is also true for fractional numbers. So let's say you have 0.3. So 1 is your multiplicative identity. So what is meant by a multiplicative inverse? So that is basically the number which when multiplied with the original number gives you 1. Okay. So for 3, 1 by 3 is the multiplicative inverse. So based on this brief discussion on additive inverse and multiplicative inverse, are you comfortable with the idea of inverses? I mean, is it clear what is meant by an inverse? Or is there some doubt? If there is some doubt, please feel free to ask. Because, of course, the R implementation is small. We can always sweep it under the rug, but it's important to know the details. So, are you comfortable with the concept of an inverse?
Yes.
Okay. Now, one important thing to remember is the definition of inverse changes with the operation that we are concerned with. Just like the definition of identity changes. So for addition, the identity was 0, and the inverse was just the negative of the number. For multiplication, the identity is 1, and the inverse is dividing that number by 1, taking the reciprocal. So similarly, as far as matrices are concerned, so let's look at our square matrix, let's say M1, M3 or M4. The inverse of these matrices would be those matrices which when multiplied with them will give me identity. Now what is identity as far as matrix multiplication is concerned? Now there is one more layer to this. When we talk about matrices, there are several identities. So let's look at the general examples. So let's call it ID2. So ID2 is the matrix, or it's actually a diagonal matrix with its entries as 1 and row equals 2 and col equals 2. So ID2 is a 2 cross 2 matrix whose diagonal entries are 1 and off diagonal entries are 0. Similarly, you can define ID3, which is again a 3 cross 3 matrix whose diagonal entries are all 1, off diagonal entries are 0. So for M3, my identity is this guy. For M4, the identity is ID3. So we won't call ID2 the identity of all matrices. So this has to be done category wise. So now, what is the inverse of M3 or the multiplicative inverse of M3? So it's that 2 cross 2 matrix which when multiplied by M3 gives me ID2. Similarly, the inverse of M4 is that 3 cross 3 matrix which when multiplied by M4 gives me ID3. And how do we find that inverse? So this is usually covered under the mathematical subject of linear algebra, and it is again, as the size of the matrix becomes larger, the calculation process becomes more tedious. So R gives us just a simple prescription. We use this command called solve. Let's say we apply this on M3, which was a 2 cross 2 matrix, and this will give us the inverse. Solve of M3, let's store this in something. Let's call this inv3, just for inverse of 3. Now if we multiply in 3, we want to do a matrix multiplication, so be careful about that. M3. So now this is not exactly what we wanted, but this is very much approximately that. So this 1.0000 still 1, off diagonal is 0, this one is 1, and this off diagonal is minus 4.44 times 10 to the power minus 16. So this is basically 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, then 4, 4, 4, 0, 8, 9, 2, something like this, which is, for practical purposes, it is 0. Now, why this does not come out exactly 0 is because of the way fractional numbers are stored. So, instead of this 0.6666667, if this would have been 2 by 3, and similarly, this guy also written as something divided by 3, then the multiplication would have been more proper, but you get the idea. So, solve M3 gives you the inverse of M3. And inverse of M3 is that matrix which when multiplied with M3 gives you the identity. Or in this case, approximately gives you the identity. But this procedure is a bit demanding on the, as far as calculations are concerned. So this usually takes more and more time as the size of your matrix increases. This is also an interesting thing. So this says that system is computationally singular. There's a reciprocal condition on one of the numbers. So what is happening? Not all square matrices are invertible. So being a square matrix is not a sufficient condition to find an inverse. So what is the analog of this? Like the examples that we were considering, additive inverse or multiplicative inverse. So if you look at 0, and we want to multiply 0 with something, let's say x, which gives me 1. Now, what will this suggest? This suggests that x should be 1 by 0. But 1 by 0 is infinity or not defined. So in those cases, we say that there is a singularity. So singularity or infinity is basically the same concept. So this can happen with matrices as well. That when you have a matrix, there may not exist another matrix that if you multiply the two of them, you get an identity. And that is what is happening with this example here. So system is computationally singular means that M4, there does not exist any inverse for M4. Okay. Now, of course, there are other ways to check this. So, say there is something called a determinant. So, let's compare what we get for the determinant for M3 and determinant for M4. So, simple terms, determinant is, so for a 2 cross 2 matrix, the determinant is simply defined as this 5 times 12 minus 8 times 9. For this guy, 3 cross 3 matrix, it becomes more complicated. You keep this 1 in your hand, forget about the row and column in which this 1 is sitting. You do 5 times 9 minus 6 times 8, multiply that with this 1, keep it aside. Then you take this 2, forget about the row and column in which this exists. You do 6 times 7 minus 4 times 9, multiply that with 2, add this to the result that you had previously obtained, and you take this 3, forget about its row and column, 4 times 8 minus 7 times 5, multiply that with 3, add that with the previous result. What you are basically doing is you are taking antisymmetric products. So if you expand the full thing, what that will be is that you're taking 1 1 1 1 1 1, that's one product, but now you take 1 1 2 3 3 2, oh sorry, that 1 1 2 2 3 3, then 1 1 2 3 3 2. So every time you do this exchange, so you flip a sign. Now this is a 9 element matrix. So this is a complicated operation, but the result is simple, and this result basically tells you whether there will be a singularity or not. So for M3, we see that we get a well-defined number. So minus 12. This is, you'll be able to find an inverse. So this det is short form for determinant. For M4, you see that this is a very small number. It's almost 0. So again, this is not exactly 0 because of the way floating point numbers are stored or handled in R. But you can assume that this is 0. And if determinant comes out to be 0 or a very small number like this, you will not be able to find the inverse. Now, of course, there were additional operations discussed, the eigenvalues and eigenvectors, but again, that also requires some time, and we have already 20 minutes past time. So what I'll do next time, since this week's lectures ended with logical operations, comparisons, truth tables, basically Boolean criteria, so we'll make that our starting point, because if you look at the week 5's material, week 5 basically introduces you to what is known as control flow in a program. And control flow is basically how you make decisions in a program. So if this is greater than this, then do this. If this is smaller than this, then do that. So control flow builds on this logical operations, comparisons, and so on. So we will not start with logical operations today. So we'll basically conclude our discussion at this point. And again, I must remind you, we will not meet on 27th August, Saturday. We will meet on Tuesday, 30th of August. Okay, I hope you remember that. And
Yes, sir.
the Google Meet link will be the same, which you receive every week from the course organizers. And I think you will get an email on Tuesday. You will not get an email on Saturday, most likely. But even if you get an email on Saturday, please remember, there is no discussion on Saturday. So, any more points that you want to clarify or confusions? If not, then I'll say goodbye to all of you and I'll end the discussion here.
Thank you, sir. Bye-bye.